Hi, this is the solution for problem 120. For this problem, 3 unit cubes with dimensions 1 by 1 by 1, they are unit cubes, are uniformly compressed between two rigid plates with an aggregate force of P. The change in height is the same for all 3 cubes. The 2 outer cubes are made of material A, while the inner cube is made of material B. Both of the materials are linearly elastic with Lamiper constants of, as shown on the board. So the problem here is to find the force P required to change the volume of block B by 3% of its original volume, and also to find the area of the compressed face of the outer blocks, which is made of material A.
Okay, the first step involves calculating the force on all the 3 blocks, the force P, and the way to go about it is as follows. We know that the change in volume by the original volume is equivalent to the trace of the strain tensor for small strains, and since we know that the original volume is 1 because it's a unit cube, it can be said that the change in volume is directly equivalent to the trace of the strain tensor, which is given to be 0.03. And since it's a compressive force, we add a negative sign, so it becomes minus 0.03. And the stress tensor is represented as follows. Since it's a uniaxial stress, it has only one component and all the others are 0. And we know that the trace of the stress tensor and the trace of the strain tensor are related by that expression shown on the board. So using that, we find the trace of the strain tensor, which is nothing but the S11 component of the stress tensor, is equal to minus 165 psi. Okay, now that we have calculated the stress on block B to be minus 165 psi, we also need to find the stress on the other 2 blocks, and that is done taking the following approach. We know that the components of the stress tensor and the components of the strain tensor are related by this equation shown on the board. So using that, we find the E11B component of the strain tensor. And now we know that all the 3 blocks undergo the same displacement, and since they have the same initial conditions, they also have the same strain tensor. So EA is equal to EB. So from that we conclude that the E11B component of the strain tensor EB is equal to the E11A component of the strain tensor EA, and so we find that to be minus 0.0375, and then after that, making use of the Poisson's ratio concept, we find the other 2 components, that is EA22 and EA33. Here it must be noted that we can make use of the Poisson's ratio only because the force applied here is a uniaxial force. It cannot be used in all the other conditions. So from that, we calculate the trace of the strain tensor EA to be minus 0.01875, and we know that the stress tensor SA has a similar shape as that of the stress tensor SB, has a similar form. So from that, we calculate the trace of SA, which is nothing but the S11A component of the stress tensor, from the relationship between the trace of the stress tensor and the trace of the strain tensor. So we calculate the trace of the stress tensor SA to be minus 93.75 psi, and from that we go on to calculate the force on the top surfaces of each of these blocks, which is nothing but the value of the stress actually, because the area of the top surface is 1 into 1, which is 1. So the force P is equal to minus 165 psi minus twice 93.75, which is minus 352.5 lb, or it can be stated as it's 352.5 lb in compression.
In order to find the final area of the compressed face of the outer blocks, we'll take one of the blocks, which is block A, and as you can see, due to the stresses and the resultant strains, the dimensions of the compressed face of the block has changed to somewhat like this. And then from this, we can calculate the area, which is simply the deformed length and the deformed width. And using the strains in the appropriate directions, we get that the area is 1 plus 0.009375. The whole term is squared because it's the same in both directions, and we get a final area of 1.0188 inches squared.